Alright, the mechanics of mathematical induction. So here's the basic idea. We need to do the following. We have some proposition, let P of n be some proposition. And for this case, I'm just going to say where n is some integer bigger than or equal to 1. For the De Morgan's case, maybe n is bigger than or equal to 2, but we put some restriction on the range of n's, and P of n is some proposition that depends on n. For example, P of n could be the proposition that the sum of the first n odd numbers is equal to n squared. So let's write this down. Let P of n be the proposition the sum of the first n odd integers equals n squared. So in other words, 1 plus 3 plus 5 plus up to and including 2n minus 1 equals n squared. That's what Pn is. So what does P3 say? P3 says 1 plus 3 plus 5 equals 3 squared. P4 says 1 plus 3 plus 5 plus 7 equals 4 squared. Each Pn is a statement. It's a declarative statement that's either true or false. That's what makes it a proposition. We want to prove that P of n is true for all n bigger than or equal to 1. Alright, here's what we can do. Step 1, prove P of 1 is true. This we call the base case. Step 2, prove that P of n implies P of n plus 1. That's called the inductive step. If we know that P of 1 is true, and we know that P of n implies P of n plus 1, this is for n bigger than or equal to 1, then we can conclude P of n is true for all n bigger than or equal to 1. That's what mathematical induction states. It states that if we have a proposition, we know it's true for some base case, and we know that if it's true for n, it's true for n plus 1 for all values bigger than or equal to that base case, then we know P of n is true for all values of n bigger than or equal to that base case. And these things are all slightly different from each other. This is the proposition that 1 is equal to 1 squared. It's a particular proposition, P of 1. This is itself a proposition which says if the sum of the first n odd integers is n squared, then the sum of the first n plus 1 odd integers is n plus 1 squared. That's what this statement says. We don't know if that's true. This says the sum of the first n odd integers is n squared for all values of n bigger than or equal to 1. And we don't know if that's true either. But this is not the same thing as this. This is saying if for some n we know P is true, then we also know P is true for n plus 1. That is by itself totally different from saying for any n P is true. This is a much stronger statement. This is saying Pn is true for all values of n bigger than or equal to 1. This is saying if P is true for this value n, then it's true for the value n plus 1. It's a much weaker statement. But this is usually easier to show than this. Mathematical induction says if we can show this weaker statement plus a base case, then we can conclude this is true. And why does that work? Because if we know P of 1 is true, and we prove this, this means P of 1 implies P of 2. So P of 1 plus this tells us P of 2 is true. And if P of 2 is true, P of 2 implies P of 3, so P of 3 is true. And if P of 3 is true, P of 3 implies P of 4, so P of 4 is true. And if we do this enough, we can eventually show that P of 17 million is true. And in fact, we can show that P of any number bigger than or equal to 1 is true by just repeating this process enough times. So the real trick in mathematical induction proofs is usually step 2, the inductive step. So let's apply this to this proposition P of n, that the sum of the first n odd integers is n squared. So P of 1 says the sum of the first odd integer, which is just 1, is equal to 1 squared. And we know that's true. 1 is equal to 1 squared, so that's a true statement. All right, let's prove the inductive step. So suppose P of n. Well, if P of n is true, then we know 1 plus 3 plus all the way up to 2n minus 1 is equal to n squared. We want to prove P of n plus 1 is true, so we want to prove something about the sum of the first n plus 1 odd integers. Well, here I've got the sum of the first n odd integers. Let me just add one more integer to both sides of this. So 1 plus 3 plus 2n minus 1 plus, let's add the next odd integer, 2n plus 1. And that's going to be equal to the right side plus 2n plus 1 over there. And now all I have to do is notice that this is n plus 1 squared. And so simply by assuming P of n and using algebra, we've shown that this, which is the sum of the first n plus 1 odd integers, is equal to n plus 1 squared. Well, saying the sum of the first n plus 1 odd integers is n plus 1 squared, that is P of n plus 1. P of n plus 1 says the sum of the first n plus 1 odd integers is n plus 1 squared. And we just proved that. So P of n plus 1 is true. And now we say, therefore, by the principle of mathematical induction, because P of 1 is true, and because P of n implies P of n plus 1, and we just show that if we assume P of n, we get P of n plus 1, therefore P of n for all n bigger than or equal to 1. And that proves that this proposition is true for all integers greater than or equal to 1, using mathematical induction. That's really all there is to it. The whole trick is sort of finding how you make this leap from here to here. In this case, the trick was adding 2n plus 1 to both sides, and then it falls out. Let's take a look at another example of this.